Hello everyone. This is Gayatri Priya, Assistant Professor in the Department of ECE of RMD Engineering College. In today's session, we are just going to discuss about a topic on VLSI design, that is pipeline. Yes. So pipelining is the concept we have already discussed in various semesters and also in various courses. So what is a pipeline? So actually it is used to accelerate an operation. That is, it wants to speed up the operation of some data path. Okay, so without having any conflicts, it is used to accelerate the operation. By utilizing such pipelining, what happens in the sense, the overall throughput will be increased. That is, whatever the operations we are going to perform, that is going to be divided into small subdivisions, and all the subdivisions are going to be carried out in a cascaded manner so that there is no overlapping and also the timing issues are being overcome. Right. So in this pipelining, let us have a reference design. Okay. So here we are going to take two inputs. One is A, the other one is going to be B. Since I'm going to have some array of inputs. Okay. For example, I can take some 15 number of A numbers and 15 numbers in B. Okay. So all these things are going to be stored in a register. So these are going to be the temporary register. In order to invoke the register, we are applying a clock, right? The first element is nothing but an adder. That is, the LSB of A and MSB of B is given as the input for this adder. So once A0 and B0 are added, they are passed on to an absolute circuit. Absolute circuit in the sense, it is just going to calculate the absolute value of A0 plus B0. That is, modulus of A0 plus B0 is calculated and it is passed down to a logarithmic circuit where it is going to find out log of modulus of A0 plus B0, and it is going to be stored in the register which is going to be connected to the output. Likewise, I have to repeat for 15 times. Okay. So out of all these 15 data, we should not have any conflict. Okay. All has to be carried out in proper phase. Okay. So and this is a pipeline design. So what is the pipeline design? The same reference design, but we could see at each and every logical operation, that is in between this adder and absolute. In between this absolute and log, we are having a register. Okay. So this register is capable to produce A0 plus B0. And this will give you absolute value of A0 plus B0. And this will give log of absolute of A0 plus B0 for the first thing. Right. So what happens in the sense, whenever I apply the first clock, this A data and B data will be fetched. That is, A0 and B0 will be fetched and it would have been given to the adder at the first clock. Whenever the next clock is given, what happens? So this A0 and B0 will be moving to this absolute value. And the next input, A1 and B1 will be fetched and it will be added in this adder circuit. When we apply the next clock, what happens? The A0 and B0. Okay, now the absolute value is found and then it will be moving on to this logarithmic function. So that it will give you log of modulus of A0 plus B0. At the same time, we would have calculated what is modulus of A1 plus B1. At the same moment, A2 plus B2 is being calculated. So this process is repeated. Okay, until all the data in A and B are fetched, added, founding the absolute value, taking the logarithmic value, and it is being given as the output. Okay, by doing so, we could avoid the conflicts between the data. So in order to perform a very high performed data path, we will be making use of this pipeline. So this pipelining in VLSI can be explained in two different ways. One is latch versus register based pipelining, and the next one is going to be NORA CMOS. NORA stands for No Race CMOS, right? In today's sessions, we are just discussing about latch versus register-based pipeline, right? It is going to give more flexibility in implementing the pipeline design. Here we could see a diagram. Okay, so here a logical operation F and G are going to be operated. Okay, so this is nothing but a transistor. Okay, or simply we can say the fast transistor. Here we are applying a clock, and next we will be applying a clock bar. Clock bar. This will be coming subsequently, right? And the output will be stored in the temporary storage device capacitor C1, and here the capacitor C2. Whenever the clock is 1 and clock bar is 0, what happens? The data will be made use and it will be available at capacitor C1, and it is utilized to compute this logical function F. Right? Whenever the clock moves from 1 to 0, that is clock bar moves from 0 to 1, so the data that is being computed at F will be transferred to this C2. Now C2 is responsible to give the input for the computation of G. Okay. So and again, when clock and clock bar is going to be 0 and clock bar are going to be 1, it leads to some overlapping of the signal. Right? So we are told when clock is 1 and clock bar is 1, each and everything will be taking care about the computation F and G in their respective time. But what happens when both the clock equal to 0 and what happens when both the clock bar is equal to 0? Okay, that can be explained along with the C-square MOS circuit. C-square MOS in the sense clocked CMOS circuit. Okay, so here what happens in the sense, in the place of the computation of EF, we are just replacing it by means of a CMOS inverter. Right? So whenever we are going to give the signal, both clock and clock bar is equal to 0, you could see this clock bar is becomes inactive. Okay, so that the signals, the voltage across the C1 will be transferred like this, and voltage across C2 will be transferred like this, thereby making a fast